Hello and welcome back. Today we get into section 4.2 on the real zeros of a polynomial function. Okay, so we're going to relate what we're doing with algebra to what you've already done years ago with arithmetic. So eventually they showed you that not every division problem turned out nice and even, and sometimes you got a remainder over your original divisor. We're going to look at some functions that work that way as well. So if we take f of x and divide by g of x, g of x, we get some quotient plus some remainder, which we can place over the original divisor. Now, just like we had rules of how the remainder and divisor related to one another in our arithmetic days, specifically the remainder had to be smaller in value than the divisor. Here the degree of r has to be less than the degree of our divisor, in this case g of x. Now, a little corollary to that. Corollary is sort of an immediate result. So an immediate result from this, if the degree of g of x is 1, degree of r of x must be 0, i.e. a constant or the zero polynomial. We can't have a negative degree, otherwise we're not looking at a polynomial function. So when we sort of checked our division problems, we typically would check the division with multiplication. So one like this, we would do 1 times 7 and add the remainder. So similarly, on our polynomial division problem, we would take our quotient, multiply by our divisor, and add our remainder, and hopefully end up with the original function. So now we're going to let our divisor be of the form x minus c. So c here is just some real number. So then we have q of x by x minus c plus r of x is f of x. And if I look at what happens when I plug in c, if I look at what happens when x is equal to c, I get q of c equals c minus, or times c minus c plus r of c equals f of c. Well, c minus c is 0, so that drops this entire term out of it, and we get that r of c is equal to f of c. So what that tells us basically is that if we have something of the form f of x and we divide by something of the form x minus c, then our remainder is f of c. So we know that without doing any long division, division or even any synthetic division. We just have that from our little theorem there. So for example, if f of x is x squared minus 5x plus 16, and I want to know what happens if I divide by x minus 1. That would just be f of 1. So in this case, our remainder, 1 squared is 1, 1 minus 5, negative 4 plus 16 would be positive 12. And you can confirm that using synthetic division. Line division works as well, if you'd like. So bring our coefficients. If you need to review synthetic division, now's a good time to do so. So there's our remainder of the positive 12. So it doesn't tell you what all of the other parts of your quotient will be, it just tells you what the remainder would be worth. One more corollary to the remainder theorem. If f of c is equal to 0, that means also our remainder is 0, then x minus c is a factor of f of x. So if we divide it out, get no remainder, then we have something that is a factor of f of x. So for example, if we know f of x is x cubed minus 3x squared minus 34x plus 42, and I want to figure out which factors we have. From a given list, so we'll say they gave us a list of x plus 3, x minus 1, and x minus 7. And I want to know which of those is indeed a factor of f of x. I would just find f of negative 3, f of positive 1, and f of positive 7. Plug and chug in the calculator from there. So f of negative 3, store as our x. And then we have x raised to the third minus 3x squared minus 34 times x plus 42. We get a 90 out of that. Trying to store the 1 as x, second entry again. We get a 6 out of that guy. And trying out the 7 as our x. Second entry, we get our nice, neat, pretty 0. So x minus 7 is a factor of f. If they ask us to further find the factored form, there's where we can just use our synthetic division then to find the rest of it. So our coefficients, we had a 1 in front of the x cubed, a negative 3 in front of the square, a negative 34 in front of the first power, and a 42 as our constant. Remember, if you're missing any terms on here, you do have to fill in the missing zeros. equivalent to if you're dividing something into 12 versus 102 if you're missing one of the place values or missing one of the terms. You do need the zeros on there. All right, so we bring down the first number, multiply and add. 1 by 7 is 7, negative 3 plus 7 is 4. 7 by 4, 28, negative 34 plus 28 is negative 6. 7 by negative 6, negative 42. And 42 minus 42, there's our remainder of 0 that we expected to see. So now we know f of x is x minus 7 by x squared plus 4x minus 6. And this one, not factorable over the integers, but we can still break it down a little bit more. You can just find the zeros. So leading coefficient of 1, even in the middle. Completing the square is going to be faster. So half of 4 is 2. 2 squared is 4. So x plus 2 quantity squared is 10. So x plus 2 quantity squared under square root is equal to plus or minus square root of 10. Yes, you need the plus or minus even on that first step. X plus 2 is plus or minus root 10. So x is negative 2 plus or minus root 10. So then that means if these are the zeros, then x plus 2 minus root 10 is one of our factors. And similarly, if x equals negative 2 minus root 10 is a 0, then x plus 2 plus root 10 is also a factor. So they're not always nice, neat, pretty integers on the end here. But just like if we had, for the sake of argument, let me switch variables so we don't get them confused. P minus 4 by P plus 2 equals 0. P equals 4 or P equals negative 2. So if these are the zeros, their opposite signs are factors. One more theorem. Polynomial function of degree n we'll say at least one has at most n real zeros. Now it's not guaranteed we have all of those. That's saying the most that we could possibly have would be n real zeros. So if it's a second degree, a quadratic, it's possible for us to have no real zeros at all. In other words, we miss the x-axis entirely. We might have just one real zero. But the most we can have is 2 real zeros. Now this next one, very powerful tool in equation solving. So we'll assume we have a polynomial function in descending order. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a naught. So x to the first, x to the 0 power on those last guys. If p over q in lowest terms is a rational 0 of f. And p is a factor of a naught. Q is a factor of a sub n. So for example, f of x, we'll go with 2x cubed, sorry, not squared, 2x cubed minus 13x squared plus 19 times x minus 6. First, I'll find the list of p, the list of q, then I'll find the ratios of them. So p factors of -6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all the possible factors of 6. Q, this is already in the right order, third power, second power, first power constant. So factors of 2, plus or minus 1, plus or minus 2, and that's it. So then the possible rational zeros all the combinations of p over q. So we have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 6 over 1, plus or minus 6 over 2. Now we'll do a little bit of simplifying and cleaning up on this list. So we have plus or minus 1, plus or minus 1/2, plus or minus 2. 2/2 is 1, we've already got that. Plus or minus 3, plus or minus 3/2, plus or minus 6. 6/2 is 3, that's already on the list. So here are our possible rational zeros. So it doesn't guarantee that they exist, it just guarantees that if they do exist, they're on this list somewhere. Now, as far as finding the real zeros of the polynomial, first we find this list of possible rational zeros. Then we plug these guys in until we find one that has a remainder of 0. So recall the remainder theorem. If we're dividing by something of the form x minus c, our remainder is f of c. So we find f of 1, f of -1, and so on. So in this one, a little bit of plugging and chugging, we find f of 3/2 is equal to 0 in our original function f. And we can use that rational 0 to find the rest of them. So here's our 3/2, our coefficients, a 2, a -13, a positive 19, and a -6. Bring down the 2, multiply and add, multiply and add. So half 10, 5, 5 by 3, 15. That's a 4, half of 4 is 2, 2 by 3 is 6. There's our 0. So now we can say f of x is x minus 3/2 by 2x squared minus 10x plus 4. So we've already got the 0 from this factor, so now we're just concentrating on this guy. This is just a quadratic. So here, let me just copy what we had on the previous page. X minus 3/2, 2x squared minus 10x plus 4. Further, we can factor a 2 from that. So we can find the other real zeros from this guy. So here leading coefficient is 1, but we have an odd middle coefficient. It might be quicker just to do quadratic formula for that last pair. So an x is positive 5 plus or minus square root of b squared 25 minus 4 times 1 times 2. So a and c respectively, all over 2 times 1. So x is 5 plus or minus square root of 25 minus 817 all over 2. So those are real zeros. So real zeros of function f, x equals 3/2. X equals 5 plus root 17 all over 2. X equals 5 minus root 17 all over 2. So we have all of our possible zeros from this. Now we could also even use this result if they ask us for the fully factored version. They won't usually ask for both. They can ask for one or the other, occasionally both, usually one or the other. It's good to know how to do both of those. So then f of x, 2 by x minus 3/2 by x minus 5/2 minus root 17/2 by x minus 5/2 plus root 17/2. So we're just flipping the signs, similar to how if x equals 3/2 was a 0, x minus 3/2 was a factor. Now, one other fun tool we have in this section is the intermediate value theorem. This is actually something that your calculator uses in its hardware when it's working with the graphs, when you're having to do calculations, for example, finding an intercept. Let f be continuous on AB. If the product of f of a and f of b is less than 0, then this backwards capital E stands for there exists. Then there exists C on this closed interval AB such that f of C is equal to 0. So it guarantees existence. It doesn't guarantee it's easy to find. It just guarantees that it does exist there somewhere. So the reasoning behind this, these are y values. The product of the y values is less than 0. In other words, they have opposite signs. Less than 0 is negative. So either f of a is positive and f of b is negative, or vice versa. If f is continuous on this interval, without loss of generality, we'll assume f of a was the positive, f of b was the negative. If this is a continuous function, if I'm going to draw this, eventually I have one of two options. If I want to touch that other point, I either have to make a jump, but that would violate this idea that we're continuous, or I'm going to have to plow right through that axis, in which case there is our value of C. So it doesn't mean it's easy to find. It doesn't even mean that it's unique. We might have that root and we might have this root connecting those 2 points. All it guarantees is that there's at least one 0 on that interval somewhere. All right, so some problems to try out in 4-2. I would recommend 1 to 19 on the odds, 33 through 43, also odd. Let's see, we have 51 to 67 odd, 75 to 83 odd, and if you want a challenge problem, 111 is an interesting problem, and I'll try to make a similar set for the My Math Lab folks. If you have any questions, please get in touch. Otherwise, I'll see you next time.